Oh, that's one way to do it. All right. So finally up on live stream. What questions you guys got for me? I'm assuming you can hear me. You guys getting the audio on your end? Oh, excellent. Abby, as you'll notice, I have something resembling a real whiteboard now. So it actually erases and, does what it's supposed to do. We're not waiting for anything. We're just waiting for questions at this point. pH and POH. All right, bring it up. So the one asking is if pH, if the concentration of H plus is 0.00457. So that work? Oh, rub a sign from KB. Oh, it's going to take me a little bit longer. Little sign. All right, pH from PKB. Just one more minute. Okay, so the first problem from that set, what is the POH and pH if we have a solution that is 0.2 molar ammonia, 0.0149 molar ammonium chloride, and the PKB is 4.74. So this type of problem, bases are really solved the same way acids are solved. They are just more steps involved. So it's still an equilibrium problem. You still need the three things. You need your K, Q equals Q, you need your expression for Q, and you need your IC table. So if we're working under basic conditions, we're pretty much almost always going to be working with the Bronsted definition. So reaction is our base, and I typically write the base or the acid first and the conjugate second just to kind of keep that pattern going for you. If we have NH3, it's going to act like a base by forming ammonium. And hydroxide. So we've got the reaction. We have our KQ equals Q. Q in this case, the concentration of NH4 times the concentration of OH minus over the concentration of NH3. And instead of Ka, we're going to have Kb because we're working underneath basic conditions. So we've got the two conditions. We've got our expression for Q. We've got them equal to each other. Our IC table is going to look really akin to the acid-base problems or the acid problems. So our ammonia, we start with 0.2 molar. We're going to assume all the hydroxide instead of all the H plus comes from our base and not from water. The NH4 plus is 0.0149 molar. Changes minus X, X, and X. So we get 0.2 minus X, X, 0.0149 plus X. Now, what we're being asked to find are both the POH and the pH. And this is actually kind of done for your benefit. POH is the easiest thing to get off. If we know the concentration of OH minus, then our POH is just the negative log of the concentration of OH minus. And if we want to find the pH from that Blair diagram is just 14 minus the POH. So with bases, there's a lot more steps involved, but conceptually, it's still the same thing. You're going to still build that IC table, figure out what parts you need or which parts you're building from, and then solve for the unknown component. So in this case, we would just stick in our E row. So here we have KB equals X times 0.0149 plus X all over 0.2 minus X. We would solve for X. We're only going to use the root because we're forming hydroxide. We need the positive concentration. Take the negative log of that number. That will give me the POH, and subtract that from 14 to give me the pH. So that answers your question? Bases are harder to work with in the sense that there are more steps, but conceptually, it's still all the exact same approach. You've still got to build your IC table. You still got to do all that work. So there's no way around it. Repeat that step again. So you're going to build your IC table. You're going to solve for the extent of reaction X to figure out the equilibrium concentration of ammonia, OH minus, and NH4. And then because we want the POH, we know that the extent of reaction equals the concentration of the hydroxide. We're just going to take the negative log of that number, and that will give us the POH. And then to find the pH, if you go back to that Blair diagram with the four corners and the arrows connecting them, to go from POH to pH is just 14 minus the POH. I'm going to try to step out of the way so you can see it. Yes, because X equals the concentration of hydroxide. So the question is, does POH equal the negative log of X? In this case, yes. Correct. So you're going to have to use the quadratic formula to find X. The nice thing is there's going to be a positive and negative root. Since we know that X has to be positive because it equals the concentration of hydroxide, we're just going to go with the positive root. It's definitely not the negative log of KB. Negative log of KB is just the PKB, which is what you're given in this problem. So your pKb was given to the problem as 4.74. Now this you do need to convert to kb before you put it in here. So you would take 10 to the negative 4.74 to get you the actual value for kb. Page 16 in the study guide. Let's see what page 16 is. So in the study guide, there are shapes of titration curves, and the question is, which one are you looking at? And that was related to the question that you actually answered today for the discussion board. So when it comes to titrations, there's all types of combinations. So we're going to use the abbreviation. SA is strong acid. SB is strong base. WA is weak acid. And WB is weak base. So we'll start simple and we'll look at a strong acid versus a strong base titration. So for a strong acid versus strong base, our pH equals 7, when we reach the equivalence point for a strong acid, strong base titration, they are the same pH. And this is because neither of them forms a salt that would be acidic, basic, or neutral. Well, they'll only form a neutral salt when they finish. So when we do the titration, we get something that looks like this. Now, a few things to notice about a strong acid, strong base. First of all, this pH scale here, the magnitude of the pH, strong acids aren't necessarily very low pH. It depends on their concentration. The big thing here is that we always have what's called a positive curvature. So a curvature, if you had a bowl, it'll tell you if the bowl is up or down. So if we have a positive curvature, the bowl is always up. After the equivalence point, we have a negative curve. The bowl is always down. Now this is in contrast to, let's see if you can see this one. In blue, a weak acid versus a strong base. So for a weak acid, the equivalence point is actually at a pH greater than 7. And the reason being is that when we react away all the weak acid, we're only left with this conjugate base. And as the name implies, a conjugate base makes the solution basic. So at equivalence, our pH is greater than 7. Now, early on in the titration, we actually see a curvature flip. So we start out with a negative curvature and we finish with a positive curvature. Your midpoint, where your pH equals your pKb or pKa, this is where we see the change from a negative curvature to a positive curvature. So your midpoint here is an inflection point in the graph. Now, in the strong base region, we still see this negative curvature. But the big tip off that you've got a weak acid versus a strong base is that you actually see, starting out with a negative curvature, it flips to a positive curvature, and then you end up with negative curvature. Versus a strong acid, where it'll always be a positive curvature until you hit the equivalence point, which point it'll flip to negative curvature. So if we look at the first one in the study packet, I'll draw it over here. It's very clearly only got positive and negative curvature. So we would say that this is a strong acid versus a strong base titration. Whereas if we go to the next problem, we see this shape. Sure, I'll see what I can do. I'm also kind of running out of camera cord too. So the other one we can do is a weak acid versus a weak strong acid. So a weak base versus strong acid. It's going to look just like a weak acid titrated against a strong base, just flipped over the pH equals 7. So this might be a little too much to see on a webcam. But if we have a weak base versus a strong acid, we start with a positive curvature, negative, and then we end up with a positive curvature. We still have our midpoint, which represents our inflection point from positive curvature to negative curvature. And at equivalence, instead of having a high pH, we have a low pH because we only finished with the conjugate acid, and we end up with a positive curvature. You're welcome. So all the problems on page 16 are asking you is that based on what you see, is this a weak acid versus a strong base, a strong acid versus a strong base, or a weak base versus a strong acid? Weak base is the easiest to tweeze out because it's going to start with a high pH. Weak acid versus strong acid, you're looking for these changes in curvatures. If you don't see any change in curvature, it's a strong acid. If you do see a change in curvature, it's a weak acid. All right, so any other questions there, Abby, about page 16? It's really just qualitative. Do you know what type of titration you're seeing? Oh, okay, fair enough. What don't you understand about it? Discussion board questions all the way. It's mostly the discussion board question is making sure you understand the regions of a weak acid titration. So for a weak acid versus a strong base, there are three important regions. Well, three important parts of the graph. First is the equivalence point, midpoint, and then the buffer. Now, technically, the buffer is anywhere between the starting point and the equivalence point. Practically, the buffer region doesn't quite go to those points because you have trivial amounts of either the acid or trivial amounts of the conjugate base in there. Now, these two regions are actually these 2 points are very important. So we've got volume of the equivalence and volume at the midpoint, and then we have the midpoint pH. So the discussion board was more to help you with, let me look at the name of the homework assignment. To help you with the titration curves with calculations assignment. So the midpoint is halfway to the equivalence point. So if we know the volume at the equivalence point, the volume of the midpoint is just 1/2 the volume at the equivalence point. To find the pKa of the acid, we just have to find the pH at the midpoint. So this is the Henderson-Hasselbalch equation. pH equals pKa plus the log concentration of the conjugate base, the concentration of the acid. And at the midpoint, these two are equal. So at the midpoint, pH equals pKa. Okay, see you later, Abby. Now, this region here is important for figuring out the concentration of the acid. And so there's the master neutralization formula. And let me write it over here so I've got enough space to do it. The master neutralization formula, some instructors teach this in Chem 1, some don't. Volume of the acid times the molarity of the acid all over the reaction coefficient of the acid equals the volume of the base times the molarity of the base all over the reaction coefficient of the base. So these n's on bottom here, they look like V's. These are the reaction coefficients because your acids aren't necessarily 1-to-1 with their base. Big M is the molarity, V is the volume. Now, there are special cases of this. If our acid is a solid, so if we have a solid acid, we're going to replace VA, MA with moles of acid, and the same thing's true of the base. If the base is a solid for whatever reason, we're going to replace its molarity and volume times with just its moles. So if we know the volume at the equivalence point, this is our volume of base. And typically what we're given the titration is the molarity of the base and the volume of the acid. So with those two pieces of information, at this point, we can calculate the molarity of the acid. And I think you actually have a virtual lab either next week or the week after that where you'll simulate an acid-base titration in a computer program and get used to working with the titration curves. Page 21. All right, so page 1 is actually a worked example of one of these problems. So before I go on, any other questions? So on page 21 on the study guide, in this plot, and you're given the pH is 5.10 here. pH here is 8.95. The volume here is 22.4 milliliters. Other information you're given, the molarity of the base, MB, is 0.150 molar. The volume of the acid is 30 milliliters. And you're being asked for the concentration of the acid, the equivalence point, sorry, the volume of the equivalence point, VEQ, the volume at the midpoint, and there's more down there, the pKa and the Ka. So I'm going to assume you all have got up to page 21. So let's talk about how to work this type of problem. So the volume of the equivalence point is really easy. It's whatever volume you're given on this line here. So our volume of the equivalence is 22.40 ml. By definition, and by the way this works, the volume at the midpoint is just half the volume at the equivalence point. So the volume here is 11.20 ml. Now, to find the pKa, this is the easiest one to do. We just use the Henderson-Hasselbalch relationship. We know at the midpoint, the pH equals the pKa. So the pK here is 5.10. To find the Ka, it's just 10 to the minus pKa. So whatever that number is. To find the concentration of the acid, we're going to use the master dilution formula. I think it tells you in the problem these are all one-to-one acids to bases. So what we get is that the molarity of the acid, I'm sure you can see this, volume of acid over coefficient of the acid is molarity of the base, volume over the coefficient of the base. Both of these are 1 in the problem statement. Don't assume they always are. Make sure the reaction tells you they're 1-to-1, and if they're not, put the correct coefficients in. The volume of the acid is given to you is 30 mLs. The molarity of the base is given to you is 0.150 molar. The volume of the base comes from your equivalent point, so 22.4 ml. So all you got to do now is solve for the molarity of the acid. And pretty much all the problems prior to page 21 that are these curves are solved the exact same way. You just need to know how to fill in the blanks. So the equivalence point represents where you've neutralized the acid. So you've got a stoichiometric amount of acid and base. So you use the equivalence point because it says this is where you've actually neutralized the acid. So it tells you the volume of base required to react away all the moles of acid in the correct ratio. So that's why you use the volume of the equivalence point, is it's actually the point where you reacted the acid away 1-to-1 with the base. You know, Isaac, it was an option in YouTube to like suppress anyone that types in all caps. And I thought it also gives me the ability to suppress like certain words if I want to in the discussion board. So I thought about like randomly picking words that it just won't let you type. The 0.150 comes from the problem statement. So if you look on the packets on page 21, it'll tell you that the molarity of the base, MB, is 0.150 molar. It's just in the problem statement. It would be kind of a game, right? To figure out like what word I've like locked out for the week. How I can tell if an acid-base reaction goes forward or backwards? Well, it has to be at equilibrium first. And once it's at equilibrium, we use Le Chatelier's principle to figure out if it goes forward or backwards. So this is where the midpoint region, this is why this acts like a buffer in this region, is that we have both the acid and its conjugate base. So if we start adding base, removing the H plus, it'll go forward. If we start adding acid, it'll go backwards. Now, if we were back in test 3 material, and I gave you H plus, A minus, and HA, and I said, which way does it go? In that case, you look at your extended reaction and say, oh, is it positive or negative? If it's a negative extended reaction, it went backwards. If a positive extended reaction goes forward. Acid-base chemistry is nice and simple in the sense that it's always going to go forward. We're always going to start with initial conditions, assuming no H plus, and we're always going to take the forward route. This is kind of why the acid-base stuff is nice, simple, is a nice thing to go to after equilibrium, because it's a simple form of equilibrium. We just make it more complicated by adding pH and finding concentrations and things like that. So Elijah's asking about the connection between pH and pK at the midpoint. So let's talk about where this comes from, because biologists love this, and it's one of those things that we teach it to you, and typically when I have time to teach it in class physically, we go through the assumptions. So if we have any weak acid Ka, but equilibrium constant Ka, we have the reaction HA goes back and forth to H plus and A minus. You get that K equals Q, which is concentration of H plus, A minus, all over HA. If we take the log of both sides, we get that the log of Ka equals the log of H plus, and we're going to separate this out, plus the log of A minus over HA. Now, we pull this to one side, pull this to the other, we get the negative log of H plus equals the negative log of Ka plus the log of A minus over HA. Negative log here is just P. So we get pH equals pKa plus the log of A minus over HA together. And this collectively is what's called the Henderson-Hasselbalch equation. Now, think about the Henderson-Hasselbalch equation. It's assuming that the equilibrium concentrations for the acid and the conjugate base are roughly those of the starting concentration. Because these are defined as equilibrium values, but really, we're only given initial values. So here we're going to assume our extended reaction is a lot less than the concentration of the acid or the conjugate base. And this can get you in trouble, particularly with if you're working with something that has a very high Ka, or you're working with something that has low concentrations of acid and conjugate base. Sorry, reading a comment. So at the midpoint, we've reacted away half acid and it's formed the conjugate base. So at the midpoint, the concentration of the parent acid equals the concentration of the conjugate base. So this ratio here is 1, log of 1 is 0. So at the midpoint, pH equals pK. And that's what the discussion board was asking for, is that at the midpoint, this is true, assuming that we have sufficiently high concentrations. Does it make sense, Elijah? It's basically just a simplification of the Henderson-Hasselbalch. The Henderson-Hasselbalch equation is a rapid way to find pH and pKa, but it has built-in assumptions. And the danger with it is if you're working with anything less than 0.1 molar, it'll start giving you off values. Now, that said, the pH scale is a logarithm, so like it's not going to be that off. But just be aware there are assumptions built into that equation. To answer Isaac's questions, yes. And actually, we add that to the conjugate base as well. So for every mole of this we react away with a base, we produce another mole of this. So technically, there's two ways to create a buffer. One is you take an acid and you mix it with its conjugate base. The other is that you take the acid and you react away a certain amount of it with base to generate the conjugate base. Honestly, either way works. Just traditionally, we prefer to mix the conjugate base, so we do what the concentration is. Correct. So at the midpoint, the equilibrium concentration, the acid and base are roughly the same. They're going to be slightly off by the extent of reaction, but if the extent of reaction is small to those concentrations, they will be close enough. At the equivalence point, the concentration of the parent acid is effectively 0, and you're only left with the conjugate base. Now, say effectively, it's still a reversible reaction. So even if you react all this away with a base, there's still some of this going to go backwards with any H plus in water. But for all intents and purposes, at the equivalence point, all the parent acid is gone. We're only left with conjugate base. And basically, our concentration of our conjugate base is whatever our starting concentration of the parent acid was. Correct. So through the buffer region, they're just changing buffer region, which is between the starting point and the equivalence point. They're just changing ratios. Correct. So beyond the titration point, and actually, I drew the figure in your lab manual, and I drew the figure in the notes because I liked it. So, gotta boast about your resources every now and then, right? So if you look at a full titration curve of a weak acid versus a strong base, beneath the equivalence point, this is acid-controlled pH. And we have two regions. We have one where the concentration of the parent acid is greater than the concentration of the parent conjugate base. And then past the midpoint, we've got more conjugate base than we have parent acid. So this is why we see this singular point is that beyond the midpoint, we're getting more pH control by the conjugate base. Beneath the midpoint, we're getting more pH control by the parent acid. Beyond the equivalence point, this is excess base control. So at the equivalence point, we've added enough base to react away all the acid. Beyond that point, it's the excess reagent. So you can think about it this way. Beneath this point, the acid is the excess reagent. Beyond this point, we're in base and excess. So beneath this region, we haven't reacted away enough of the acid to stop it from being an acid. Beyond the equivalence point, it's all excess base control. So any base that we add beyond the equivalence point is just making the solution basic. Yeah, actually, let's go to the packet. So if you're looking for just the pH in the buffer region, so if you go to the packet, it's pH of an acid solution. So it wants to know the pH of a solution that is 0.145 molar carbonic acid, H2CO3, and 0.133 molar NaHCO3 if the pKa equals 3.74. It is page 7 in the packets. Now, again, this is specific to my packets just to make life easier on you. The first one is the parent. The second one is the conjugate. So this is an acid because we're given pKa. So we have H2CO3 dissociates into H plus and HCO3 minus. Actually, getting a request for a specific problem. What is the pH if a 0.5 molar solution? Okay, let's do that one instead. It's a lot easier to solve, actually. So pH, if we have a 0.15 molar solution, HIO3, iodic acid. The pKa here is 1.23. Now, buffer problems in principle can be solved with a Henderson-Hasselbalch. If you have a pure acid with no conjugate base, you can't use Henderson-Hasselbalch. So HIO3, we're given a Ka. This indicates it's an acid. So it's HIO3 going back and forth to H plus and IO3 minus 1. We need our expression for Q. We need to set it equal to Ka, so it's H plus IO3 minus 1 over the concentration of HiO3. Need our IC table. Initial concentration of the HiO3 is given to you as 0.150 molar. We're not given either of these, so we treat them as 0. Our extensive reactions and our n values. Now, you're being asked to find the pH. You've got that below diagram where it gives you pH, POH, H plus, and OH minus. Once you've got one of those, you can find the other ones. So it's asking you for pH. You're probably going to use the square that has the H plus in it. If you're working with a basic buffer, you're going to find the OH minus first, convert that to POH, and then go to pH. So stick this in. You get Ka equals x squared all over 0.150 minus x. We rearrange and solve. We get x squared plus Kax plus minus Ka times 0.150 equals 0. Stick that into the quadratic equation. Solve for x. Once you get x, that tells you the concentration of H plus. Negative log of the concentration of H plus is pH, and you're done. So a lot of stuff that goes on after you get done solving the equilibrium component of the problem. If that's what it takes, Elijah doing it over and over again, do it. Build on what you know from test 3. These are all just IC tables. So I'm going to erase this really quick. So at all of these problems that we're working with acid and base titrations with few exceptions. So they're all going to use the IC tables in equilibrium. So let's talk about that for a moment. You're always going to have the reaction. You're always going to have KQ equals Q. You're always going to have your IC table. So this is going to be at the heart of every single one of these problems. What makes these the only thing to really make these problems challenging is finding initial concentrations, finding Ka or Kb, or finding pH or POH. So every single one of these is going to go through an IC table. So if you go to the packets on page 7, the question asks, what does the molarity of nitrous acid, HNO2, need to be in order to pH of 1.74 if the pKa is 3.14? So I'm going to write these values up really quick. So this is one of those initial concentration kind of problems. Like, can you figure out what the starting concentration needs to be? And honestly, these are some of the easier problems to solve. So we're looking at nitrous acid, HNO2. So HNO2 dissociates into H plus and nitrate or nitrite. We've got the Ka equals concentration of H plus, concentration of nitrite, over the concentration of H in O2. And we're going to have to build our IC table. And we're being asked to find the initial concentration, which is this square here. We're not given any initial concentrations of H plus and NO2 minus. This pH here represents an equilibrium value. So it's going to show up, but it's going to show up further down the table. Changes, minus X, plus X, plus X. And we've got our pH equal to 1.74. So this means our concentration of H plus here is 10 to the minus 1.74. So let's throw in a dummy variable for the concentration of nitrous acid. So let's just say this is A. So we get A minus X, X, and X. We know that the concentration of nitrite here equals the concentration of H plus, which is 10 to the minus 1.74. And we know from this equilibrium value that X equals 10 to the negative 1.74. So if we plug this row in here, we get Ka equals X times X all over A minus X. If we rearrange and solve, we get that A equals X squared plus Ka times X all over Ka. We know X from the pH because the pH connects us to the H plus concentration, which connects us to X. We know the Ka because it's given to us in terms of pKa. So all we have to do is plug in and solve. These problems only get harder if I ask you for a mass per volume, because if I say, well, what mass of nitrous acid is needed to make a X liter solution, which I think is one of the next problems, there's a further step that molarity equals moles over volume, and moles times molecular weight equals grams. But these are not problems related to solving the pH or relating to the IC table. These are all periphery problems that kind of branch off to the side. So it's going to take all the material we covered from test 1 on working with molarity, and it's going to take what we learned from test 3 in terms of equilibrium and just create more steps. But yeah, if you're wanting a hint for the test, page 8, those would be good types of problems to know how to solve. pH under basic conditions are the hardest problems I can give you. We work predominantly with acids. It's because there just aren't a lot of bases. I mean, if you look at the tables of weak acids, there's thousands of them. If you look at tables of weak bases, there's hundreds, which doesn't sound bad, but it is. So I would say the hardest problem on this test is always figuring out the pH with a basic system. Because a lot of it, you're so used to solving for the acid concentration and solving for pH, which again makes sense. That's the majority of problems in real life. You forget to go back. Or you're so used to solving acids that you immediately set your base up as an acid, even though it cannot possibly be an acid. And I've actually started selecting my examples now. So when people write as an acid reaction, I can write a big question mark and ask, well, why did you say this was an acid? It doesn't even contain a hydrogen. But I would say those are definitely the hardest types of problems. But again, I'm not the type of instructor that gives you gotcha questions either. Like there are examples of base problems on these packets as well to give you practice with them. You're correct, Isaac. So all you got to do is solve for the OH minus concentration, find the POH, and find the pH. So conceptually, it's not that hard. And that's what I see on test 4 when I give it, is that students do the basic problem. They either think they did it wrong because it was so straightforward, or they spend the whole class trying to solve it and they can't do it. And it's because they're trying to treat a base as an acid, and it just doesn't work that way. Not as familiar with what the chapter titles are with Burge. I knew what they were for, not Burge, with OpenStax. I used to know what they were for Burge. But basically, we're working with acid bases and buffers. So to be honest with you, I don't know off the top of my head what chapter 15 is. I don't think I brought home my copy of OpenStax. So you'd have to give me examples of what's in chapter 15. Equilibrium of other reaction classes. So that's probably talking about solubility. That was the previous test. And there probably the reason why I have chapter 15 on the syllabus, if it's there, is that there are probably parts of that where they talk about acid-base equilibrium. Equilibrium of other reaction classes. We're also going to talk about electrochemistry for the final exam material. Those are all reversible reactions. In terms of other ones, KSP, solubility constants, any of the equilibriums we work for test 3 would all fall in the class of other reaction classes. So I've actually set it up so we've got live streams for every normal class period except for the test 4 exam day, which one we're not going to live stream, but there will be a live stream every Monday and Wednesday from here on out. And they're actually going to be linked in the announcement. So all you got to do is go to the announcement for that week, click on it, and it should send you right to the live stream. Date of your exam, that's a good question. Let me look it up real quick. So April 21st is the date of the next exam. Like the previous exam, you'll have a full week to take it just to make sure that if anyone has computer accessibility issues, they're going to have it. Same format. You're going to have a test that you click on, and then you're going to have time to upload your work. I will make the addendum that instead of giving you 24 hours to submit the work, you'll have up until 30 minutes after the due date of the test to submit your work. So it just kind of keeps people from like submitting their work really late. It gives me the option of grading the test pretty early. But yeah, you'll have the full week. I would not recommend waiting the full week. Just go ahead and knock it out. Redox knocks a lot of people to the ground if they have not, depending on what their background with chemistry 1 is. So if you had a chemistry 1 teacher that really talks about redox a lot and balancing redox reactions, this material is easy. If you haven't had a lot of experience balancing redox reactions, this gets really hard. Yeah, April 21st is the day of the next exam. Your grades from test 3 are already posted. I just haven't transferred them to the test 3 column, but your test 3 exam has already been graded. I think I got all of them graded actually. All right, it's 2 people that are good with questions, and I think there's only 3 people kind of sitting in the background. So if you're all good, I'll see you all next Wednesday. Those of you, well, oh, it's fine. This is actually, we don't even actually have to host live stream. So glad this is helping you out quite a bit. All right, if no one else has got any questions, I'll cut off the live stream. Again, you'll have access to go back to these at any time. We'll have live streams every Monday and Wednesday. Please come in, please ask your questions, and I will see you all next week.